Welcome back. In this video, we'll observe that a single value in an augmented matrix can determine the number of solutions to a linear system. Let's get started with example 3.3.3. Consider the linear system whose augmented matrix reduces to the following. Notice that this matrix has 4 columns and 3 rows. This means that the linear system that it came from must have 3 equations, each in 3 variables. The first row of the equation is 1, 1, 1, and 1. The second row of the equation is 0, 1, k, and 1. And finally, the third row of the equation is 0, 0, k minus 1, and k squared minus k. We're asked the following question. Which value or values of k affect the number of solutions to the linear system? I want to start by making a few observations. The first thing that I want to observe is to look at the leading entries of the matrix. So definitely 1 is a leading entry. And this other one is also definitely a leading entry. But the k minus 1, I'm not so sure about. So my first observation is that the system has at least rank 2. Another way to say this is that the reduced augmented matrix has at least 2 leading entries. My second observation is that the matrix is in row echelon form. I know it's not in reduced row echelon form because there's a 1 above the leading one in the second column. Finally, my third observation is that by picking k, we determine if k minus 1 is a leading entry or not. So which k value do I care about? Really, I care about the k value, k equal to 1. So if k is equal to 1, the reduced augmented matrix is the following. 1, 1, 1, 1, 0, 1, 1, 1, 0, 0. Now the k minus 1 position is going to be 1 minus 1, which gives me 0. And k squared would also be 1 minus 1 gives me 0. So let's look at what I have here. The first question I should always ask is this matrix consistent? Remember, we can tell if a matrix is consistent by looking at the column of constants, and I can see that the leading entries of the matrix are here. Neither of those leading entries is in the column of constants, so I know that this matrix is consistent. Furthermore, I can see that I have 2 leading entries and 3 variables. Therefore, in this situation, when k is equal to 1, this linear system has infinitely many solutions. Let's now consider the case where k is not equal to 1. If k doesn't equal to 1, then We can't really say anything about what the augmented matrix looked like, except notice that when I write down the augmented matrix, I know that the 1 is the leading entry, the second one is the leading entry, and k minus 1 is the leading entry. So k minus 1 is a leading entry. Since k not equal to 1 means that k minus 1 is not equal to 0. And so we have 3 leading entries and 3 variables. What does this mean? This means the system has a unique solution.